Let me know when I can go.
And you should be good. Thanks.
All right, so good morning, everyone. I'm Rebecca Ringett, and I'm presenting on behalf of a interesting distribution of people listed on the bottom there. And I'm going to be talking about a proposed solution called Liked and Diaries. And the motivation for these proposed solutions is demonstrated in the artistic picture on the right. And if you think of each of these shapes in different color sections as the various resources or the methods of access to these resources in heliophysics, then you start to become more aware of what a maze it can be for someone new to heliophysics to navigate and to find the resources that they need and plug everything together. So the Liked Diaries proposed solutions are a way to approach this conglomeration of resources that we've worked so hard to build and develop connections between them to make them more useful to others in the field. So motivation is nicely presented here. And the question that drives both of these solutions is what infrastructure would someone new to the field, whether coming up through the academic process or attempting cross or interdisciplinary research from fields outside of heliophysics, what would they need to be able to connect with our field, understand where our resources are, and start using them? And I have a few examples around here. I'm not going to talk about all of them. But for example, they would want, we need our resources such as data, models, and software and tutorials to be easily discoverable, easily usable, right? I mean, if you can find it and can't use it, you're stuck. So pulling all of these things together and connecting them in a way that's intuitive will really help make not only our work more efficient, but help to attract talent and increase our science return. So the first thing I'm going to talk about is this liked resource as a proposed solution. So let me preempt this by saying we're not trying to propose this as a strict structure of the only type of solution there is, but rather as one option of a groundwork that we want the community to add their ideas to and build upon to produce something that's the best for our field. And we're not advocating for one group to do it over another, so let me just preempt by saying that. And I'm going to go on and describe what we've come up with. So LIKE is actually an acronym. It's not just from Facebook or Instagram. It's a library, knowledge, and discovery online resource for discovering and implementing knowledge, data, and infrastructure resources. So let me tell you what I mean by that. I'm not going to go into all the details of this diagram. At the end of the presentation, there will be 2 QR codes or 2 links, whatever your preference, to get more information on these things. So feel free to investigate further there. But what I will say about the diagram here is that it presents the majority of the components that we think would be useful to link together into one place. And that linking can be done in a variety of ways. There's one method presented in the papers that are coming out. I'm not going to go into it at the moment, but the point of this diagram is that developing these connections together, such as connections between descriptions of what each phenomenon is and how it links to different variables in the data and how it links to models and what software is relevant, pulling all of these connections together into one intuitive place can help not only our ideation process for research and maybe doing cross-disciplinary from solar physics to more magnetospheric physics and so on, but it also provides the same advantage to others coming into our field. So we see this as a really useful way to connect all of our infrastructure resources together and then provide direct connections to how to actually get those components. All right. So the idea is to collectively build a central ideation resource to connect the educational content that we've all been developing on our own websites to those heliophysics resources and kind of link arms together to build something that takes less effort on the individual but pulls more in the community. The idea is to encourage the content discovery across our research areas so that we as heliophysicists can become more aware of other parts of our field and how they link together. And also, one important thing is to promote and create interactive content to attract new talent. You see this done in other fields, such as the terrestrial weather, where they have quite a plethora of interactive content, but our field is coming along, and let's pull our efforts together to build this. Now, what I'm going to spend the most time here on this presentation is this particular diagram and then a few comments towards the end. This diagram shows the second portion of the liked resource. And the goal is to put the F in FAIR, how to find stuff. So this is one idea. So the idea is to divide the types of resources that we have into categories. And you'll notice that I have resources from in this diagram from outside heliophysics. And the reason that is because this can be easily extended to connect with resources outside of heliophysics. Okay, but the idea is to categorize them into different, categories. And each of those categories would be associated with a simplistic search form, where you would search for, say, coronal mass ejections in the data and discovery resource, and you would find the archives, not the data. You would find the archives that contain data that's relevant to coronal mass ejections. And if you did the same search, say, in the software discovery search form, you would find software that's relevant to coronal mass ejections, particularly software that enables access or easy implementation for the data or for models and so on. And this also connects to the knowledge discovery resource I just showed a diagram on, and even funding and people and those kinds of connections. And the idea here is to build a system of systems, possibly in this way, with simple connections so that people can find where everything is stored instead of having to get lost in Google like that. I believe it was Allison Liu that presented a couple weeks ago. But the idea is to efficiently leverage what we already have and connect them together and even extend that to areas outside of heliophysics. Now, the colors here are kind of important. I'm going to emphasize the gray boxes because the one primary idea that we have in the two papers that have been submitted is that the idea isn't to implement a universal standard across everything, but rather to connect how it's already built. But the idea is to encourage a set of standard microservices. So what I mean by microservices would be, for example, for a data archive to have an intuitive search form so that users can search for something like solar flare data and be presented with some options of variables and time ranges and such things. And with software to be able to search for time series analysis and software in a particular language, and and find an archive that has these kinds of things, or some resource where there are some interesting tutorials that apply to those keywords. So by the different types, the different categories of archives offering the same or similar microservices, such as the ones in the gray boxes, that means that the person who finds the archive will have access to, will be able to find what they need in that archive and be able to choose wisely, right? So the quick look graphics and the data in the model archives, that can help them choose what data they want and so on and so forth. So as this liked resource is built, it will enable the how we can build a new type of resource, which several groups have already embarked upon. But this liked resource will serve as the foundation for something we call the diaries resource, which is an ecosystem to simplify discovery, implementation, analysis, reproducibility, and sharing of scientific results in environments. So I'm going to glaze over this in interest of applying these ideas to PyHC as a software archive at the end. Okay, so here's a simple graphic of what the diaries ecosystem is and what services it offers once it's developed. So the discover aspect is built directly upon this liked resource. Built on top of by implementing an encouraged standard of microservices, it makes it possible for such an ecosystem to offer users to be able to implement the data or software or whatever of their choosing into this ecosystem by simply clicking a button. Because by developing those standard interface, the standard microservices, then this layer on top can just interface with whatever that access point is, such as the happy interface, for example. Right? And then it builds upon current technology that we already have, such as Sean showed yesterday, to build in the analysis, in virtual collaboration, where you can preserve your analysis with an automatically containerized ecosystem. And the thing I find most exciting is the share component, which is here on the bottom right corner. I'm not going to talk about all of this. You can see the links for more information later. But where you'll be able to create custom interactive tours of your analysis to share with colleagues or share with the operational side of things, and virtually collaborate at every step of your research like we're already doing, but also develop and deploy your own custom dashboards and environments, even for those that don't know Python. Right? And one goal of this is to decrease the amount of code that's necessary for someone to learn to be able to make contributions to heliophysics. Okay, so putting all of these requirements together can really enable not just fair data, but fair science. So the point is to develop simple but flexible connections, focus on a standard set of microservices, add in the current technology we have, and then we'll be building a structure together that all in heliophysics, that can level the access for all in heliophysics. Now the question is, how can we apply these ideas to PyHC as a software archive? Okay, I'm going to mention a few of these. So one thing would be to develop some minimum required standards. And the point of having the standards, period, would be simply to make the software offered to users in PyHC useful and relevant to heliophysics. So what would make the software useful? Well, to have code coverage, to have simply so that we know it works, to have Python 3 compatibility. At the moment, Python 3 is the thing. I mean, we don't have Python 4, and Python 2.7 is no longer supported by a lot of things. To make sure it's applicable to heliophysics, to have some sort of minimum documentation requirement so that users can find out how it works and what it offers, and to be able to install the software somehow. And then in contrast to this, there can be preferred standards, and those preferred standards would address the question of, well, what would increase the usefulness of the software to our users, and possibly usefulness in conjunction with other PyHC software. And there are some suggestions here, such as containerizing some of their tutorials for things that they highly prioritize in their package, and pursuing interfaces with other PyHC packages, or at least interoperability with those other software packages. So if any requirement is going to be implemented, then there has to be motivation. That motivation for the software developers can be to offer services. It's typical for any member organization, right? So some suggestions are here. And some of these have already been mentioned, but in the integration strategy workshop. But one might be to offer help to these software packages to help containerize their tutorials or even containerize their software to make sure it works on any platform, to help promote that software functionality to the broader heliophysics domain and even outside of it, and provide opportunities for funding for improvements to that package. So I'm going to close it here. I think I'm out of time. But the current distributed structure of our resources, there's been a lot of effort to connect these, and if we can coordinate our efforts, then we can make the science in heliophysics, that's poorly phrased, we can make heliophysics more accessible to new talent and even to ourselves by connecting our archives based on a systems of systems approach, by building on the current successes that we're already seeing in technology, and by pairing our efforts together. So you see the QR codes on top left. There's one for each of the outline paper outlines, and then if you prefer, there's links on the bottom left. So as a team, we're calling on the community to work together on developing something along these lines to launch our field into the future. That's what I have.
Awesome. Thanks, Rebecca. Does anyone have a quick question for her before we move on?
Feel free to take a screenshot if you want the QR codes.
Also, these slides have been shared in the meeting G Drive, so you're always free to go and check those out too. Let's see, I see Leslie has a hand up.
Okay.
Hi, yeah, thanks, Julie. My name's Leslie. I'm very new to the community. This is my first interaction with the PyHC group. So hello, I just want to introduce myself, but also, so this question, might be on a higher level detail that you've addressed somewhere else. But again, like I said, I'm new, so I figured I'd ask it. So the question kind of comes from this idea that when you go and get data or use software, there's typically like a rules of the road. Like all instrumentation has caveat, and there's different levels of data, level 1 and level 2, level 3. So how does that information gets translated within this network or ecosystem that you would be building to the user?
Two possible ways. So first of all, if you're in the discovery portion of this, right? So the interface I described here interfaces to a specific archive, not directly to the data. So you would get that information through one of the microservices or one of the services provided by that archive, right? And so you would get, so I hear rules of the road. So basically rules of the road typically means, okay, you're supposed to cite our data or software or whatever you're pulling from this in your research if you do use it. How to implement that data, typically that's kind of left to the user, which is of course not very useful. But there has been a lot of effort in software development, particularly in some efforts over here, but not only inside PyHC, but outside PyHC, to make that access easier and implementation easier, but it's not well connected yet.
Yeah, I noticed within your PyHC, there was sort of like a slide. There was a minimum documentation in your minimum standards. Would that include like instrument papers and stuff like that? Again, I feel like a lot of times, just, in my experience of developing a data product for the community to use, there's always these little caveats that, about the instrument or within the data that's hard to translate to the community when the data is being used. And a lot of times, it's encouraged that you have a team member from that instrument involved in your project, or at least, someone to contact about questions and issues you might have with using the data. But maybe that just comes with like the responsibility of the scientist to make sure that they're doing good work.
Well, I don't think so I'm at CCMC, which would be classified in this scheme as a model archive. And I know one of the things that's the rules of the road for us is to contact the model developer for the model data you're using to make sure that those kinds of intricacies are taken care of.
Yeah.
How much that will go away, I honestly can't say.
Yeah.
It's always good to have someone who knows the data involved.
Right.
That's always super helpful, assuming they are helpful, right? Not everyone
Right.
responds.
Sure.
But
The space, I was
there
going
was
to say,
one
the
thing.
space data descriptions are supposed to include a lot of this information if they can include.
So one of the things here in the diaries diagram that I glazed over is here. So when the data is implemented by clicking on it and it gets whatever relevant software gets installed and so on and so forth, is the citations for that data, software, etc., automatically imported. So if you're looking for papers to go read, that would be a great resource instead of having to track it down through 10, 15 links. Which paper was it, right?
Yeah.
Okay. I think that's enough. We've taken enough
Yeah.
time.
Thank you.
Sure.
Awesome. Thanks, Rebecca, and thanks, Leslie, for the excellent questions. Rebecca, I think you have a few questions in the chat. So next up, yeah, next up, we'll be hearing from Barbara Thompson about the HSO Connect website effort. Wait, Barbara.
Hi, everyone. Can you see this okay?
Yeah.
Great. So I'm going to talk about one of the microservices that Rebecca described. And it's hopefully going to help, or two of the things that really we have planned, the HSO Connect Data and Modeling Resources Portal, and also our plans for the Helio Hack Week coming up next spring. These are all aspects of what it takes to build this ecosystem. And some of these things aren't as plug and play as Pan Helio, for example, but what we've tried to do is identify the things, the way to fill the gap for some of these things that are needed. So the first thing I'll talk about is the HSO Connect portal. Now, HSO Connect is a program at NASA headquarters. It was spawned really by the launch of Parker Probe, the need to stimulate connecting coordinated observations and models to make the most of the Parker Probe mission. But it's not just Parker Probe. It really has to do with connecting and turning this suite of instruments and models into an integrated observatory, which we call the Heliophysics System Observatory. So one of the things that HSO Connect supports is a series of campaigns called the Whole Heliosphere and Planetary Interactions. This is an international initiative, and it's focused around the solar minimum period, which was just recent in 2018, 2019, to try to understand the interconnected sun heliospheric planetary system, with the reasoning that, well, if you can't understand the simple case, it's going to be very hard to understand the dynamic case. But if we focus on solar minimum, then as the sun rotates, we do get a chance of maybe understanding the 3D structure and tracing its flow out to the planets, the heliosphere and the planets. Also, when there is a transient like a CME, it is relatively isolated, or it's supposed to be, if solar minimum is behaving like we know it, which means that it's pretty clear to separate the effects of a coronal mass ejection from other structural type phenomena in the heliosphere. And it's the third time we've done this. The first one was the whole sun month, and the second was the whole heliosphere interval in the previous 2 solar cycles. So WHIPPY consisted of a number of campaigns. These were target periods where there was either something happening that was interesting, looking for recurrent coronal holes resulting in high-speed streams. There was a total solar eclipse. There were Parker perihelia, and there's also conjunctions between spacecraft like Stereo A and Parker Probe that were good opportunities to do multi-point measurements that were coordinated. And so there's a number of campaign periods that were done for WHIPPY. And just to give you an example of what we're aiming for, this is the paper from the last solar minimum this is the whole heliosphere interval before we started to include the planets. So it was just the heliosphere. And what we did is we built maps. These from 0 to 360 is the solar longitude, and -90 to +90 is the solar latitude. And so it's just unwrapping the sun so you can see it all together. And we built map after map after map of all the different contributors to the data, all the different data and model contributors. So some of these are simulations, and some of these are observations. And so we tried to build a what we call a mosaic of all of these things. We also did deep projection of in situ data in the heliosphere, and also near Earth in the upper atmosphere and the magnetosphere. And so this was one of the largest, or possibly the largest coordinated collection of data ever accomplished to study a single thing. And we're aiming bigger this time with WIPI. The great thing about this is that in 2008, when we did the last one, open source software wasn't as common. We had our software trees, but when we shared through the tree. But now it's having the Python environment has made this even easier. Now we have, just to advertise, we've had a series of show and tell days. These are video tutorials. There's a couple dozen in there now. So anyone, there's many people preparing and contributing different assets to the WIPI campaign. And so they all recorded about 15-minute videos on how to use those assets and access them. But there's, as you may imagine, we have some 700 people on our email list. We have about 200 people actively working on compiling and coordinating data. Our first workshop was just last month, where we started to talk about the science that we could approach and started to assemble the data. So you're wondering, how on earth are you going to get all that together, especially now that we're doing it virtually? In the past, we'd all sit in a room with our laptops and kind of poke at it and share the data. But now the communication is online, which has its pros and cons. So what we've done is we've designed the data and modeling portal. Now this is a portal. It serves nothing. It only connects things. And so this is one of the parts where Rebecca was talking about the need to, just find out what's there. And we try to design it so that you don't have to find the resources find you. You can set a target. So this is a database, and it's just starting. The format is very Amazon.com like. You have tabs, you have tags. You can just go ahead and flag if you want tools and coding resources. You can see, you'll see that there's Plasma Pi, there's PySat, so these are filters. If you want to focus on a particular research domain, to make sure to see the assets that correspond to only solar research, for example, or solar and heliosphere research, you can flag that. Sorry, this is a filter, so it's an and filter. It's not an or filter. Or you can look at the domain. If the domain is development of resources and tools, you can restrict it to that for groups that are developing resources and tools. And so it's very Amazon.com like. You got your filters, you can flag, and also you can just go ahead. If you're interested in Python, you can just, you can enter the keyword in here, and then you can look, and then it'll show you the Python. If you're looking for heliosphere type things, there's one thing that explicitly mentions heliosphere. This query is not very smart yet. We're going to try to track the queries and understand and start to use something a little bit more natural language processing to understand, A, help people find and identify things better, and B, just help people find the us understand what kind of queries people are looking for. So if there's something missing, we can try to identify it. So one of the things that's there is these, as I mentioned previously, these WIPI campaigns. These are the series of campaigns, and if you go to about, we have descriptions of all of these campaigns. And then we have there's a series of features that are evolving. We're still trying to define them. So if you have Jupyter notebooks, or some sort of examples, you can see them. You can find them here. If you have a GitHub site where you can directly download it, or if it's a data resource, you can download it. It's here. The web interface is here. The demo is Nick Murphy has a wonderful demo on how to use Plasma Pi. There's also people have done demos, as I mentioned previously, about the Whoopee Show and Tell. Those tutorials, those demos are here. And finally, about is usually just sort of a general information page, and discuss is often it's a GitHub issues page or a discussion site or something, a place for you to interact with the providers of that resource. And so the submit a resource works, but it throws a 500 error because, well, I should say, one of the wonderful things about this is on the NASA Amazon cloud. This is not on a NASA server, which means that we're free to do things that would be very difficult to do with an internal government website. There are vulnerabilities when you try to put something, a dynamic site, something that accesses and utilizes different resources on a government site. The Amazon cloud is pretty, it's Amazon's problem, right? But one of our problems is that if you submit a resource, you can go in here and it does have all of everything. You can load a logo, you can flag all these different things. The problem is that it does throw a 500 error because it doesn't work very nicely with the NASA mail system. So we have to move that over. We have to move that over into a different notification once the resource has been submitted. But so if you do want to do that, you can submit a resource, or you can just contact me. That's fine. It's probably easier to do that because then for sure I got it. You can see it show up. Finally, I want to do a little bit of a promo for our Helio Hack Week, and this is our so we had a Helio Hack Week in there we go. In August of 2020, there were 5 teams. There's about 40 participants. Most of them were on teams, and many were supporting infrastructure people. And we're going to do another Helio Hack Week. This is the Center for Helio Analytics. We're sponsoring. It's a newish program where at NASA Goddard, where we're trying to encourage and promote resources that allow people to do integrated data science with heliophysics resources. So one of our big projects is this Hack Week coming. It's hopefully next spring. The focus will be on community resource development. And we have some potential targets for these resource developments. Again, an ecosystem like diaries does not just grow on its own. It needs a lot of community support and development. And so what we're trying to do is identify elements that we as a team could come together to hack to start to build these resources. So one of them is, there's just ideas that are thrown out. All these newsletters that everyone sees everywhere that we keep on getting, some are online, some are emailed, yada, yada, yada. It would be great if we had an integrated an NLP-based interface to parse and store these newsletter entries so that they can be searchable, retrievable. Another aspect is I think a lot of the data science community is really understanding the importance of responsible machine learning or responsible data science in terms of explainable and interpretable, but also just the full elements of what it takes to be a responsible scientist. And so we would like to have interactive and executable examples. And speaking of that, Sean Paulson's talk yesterday was very exciting. Yes, we definitely want to move from the standard PDFs and the types of things to fully interactive publications driven by the data and model in the back. So you publish a full cube of your resources, and what is displayed is something that's interactive as part of your paper. But it's not going to go on its own. And journals have told us very clearly that they would be interested if we can develop it a little bit more. And so one of the potential topics is taking, as people who have publications, where using the elements that Sean talked about, can we set up a prescriptive protocol for a publication like that? Also, there are training examples. A lot of your instructors, a lot of people are, there's so many requests for curriculum materials and things. One of the things I think Rebecca was mentioning too, but you know, we'd like to add a binder hub so that we can have all of these examples interoperable and usable rather than just posted, so that people could just run them directly on that. So developing examples and tutorial tools, including responsible ML, would be great. Another topic is, which you guys are talking about this week, is, you know, there's still some remaining, it's particularly complex code that would be really great to have is turned into Python. And also there is, NVIDIA is one of the co-sponsors of this effort, and if they are very keen on us taking slow code and turning it into a GPU accelerated code. One of the teams last time did that, and we'd like to continue that. So here's the rough schedule. We're trying to set up an organizing committee, and the Hack Week is aimed for April to May of 2022. I would be thrilled if any of you wanted to join with the organizing committee. It's a friendly group. We're pretty low key. This Hack Week will be online. And so what we'd like to do, but the main thing is we want to make sure that the topic we choose and the resources that we target will be of use to the community, something that they will need, that the community will need, and will help people complete this the whole diaries ecosystem that's been scoped out. So thanks everyone, and I mean, I'll post the contact info on the notes doc and in the chat. Thanks.
Awesome. Thanks, Barbara. Anyone have a quick question for Barbara before we move on?
Yeah, I had a quick question about Hack Weeks. So I think Hack Weeks are great and a really good way to like make little new projects that you wouldn't otherwise have time for. But then a problem I've found in the past is that there's then a maintenance burden to keep those projects on after the Hack Week. So I was wondering if you had any experience or comment on that from the previous Hack Week, or any comments in general.
Yeah. I think it's really the important thing is having an organizing committee that understands that, doesn't choose targets that are going to die heat death from not being properly implemented. But another aspect of this is that we are the Healy Physics Data Resource Library is coming online. There are dedicated resources to support these things now. Again, our hope is that we will be able to have the binder hub up. I would like to very much see our SunPy, for example, all of our SunPy examples migrated over to interactive tutorials rather than ones that are posted, or interactive notebooks. And so there is more effort to that is working towards doing long-term support of these things. However, so it's a little bit of give and take. Healy Physics Data Resource Library is still being defined, and so what is needed can, if it comes out loud and clear, it'll be prioritized as well. And so that's the so that's not, it's not a complete answer, but and I know you've heard us say we're trying forever, but we're still trying, and the hope is that we will by having a place, a consistent home that is accessible, an Amazon cloud resource that is supported by NASA to host these things, means that the access and the maintenance hopefully won't be as bad. By the way, David, we will be able to add you to the cloud as one of the editors. So you can, if there's a resource on the cloud that is there, we will be able to add you, because it is no longer an internal government website, it's an external site.
Great, thank you.
Awesome.
Yeah, and Jack posts the RFI for the Healy Physics Data Environment. Thank you very much. That is an important thing to remind people to contribute to.
Indeed. I'll make sure to include that link in the general notes document. Thanks again, Barbara. So now we will be moving into the portion of today that is all based on tutorial brainstorming. So we'll be hearing from some of our core packages about various ideas for tutorials they might have for, making their packages better integrated, interoperable with other packages in the community and so forth. So pay close attention and see which of these tutorials you might be interested in helping hack tomorrow. So the first one who will be going is Nick Murphy with PlasmaPy.
Sure, thank you, Julie. How's my volume level?
It's great.
Okay, and hopefully that's showing up now.
Yep.
Awesome. Okay, so yes, this is going to be on tutorial brainstorming, and in particular for PlasmaPy. I wasn't quite sure how to organize this talk, but I did my best. So, and also, please feel free to start discussing these topics as I'm going. Okay, so first I wanted to give a very brief introduction to PlasmaPy. The mission of the PlasmaPy project is to grow an open source software ecosystem for plasma research and education. So we're not only a core package for PyHC, but we want to become a core package for plasma physics as well. And there are a lot of ways to become part of the community. We have office hours weekly, a community meeting, we have an element chat room. If you have ideas for new features, please raise them on GitHub. And also similar to what Barbara was saying, if you want to help organize next year's Plasma Hack Week, which will probably be during the summer, you're very welcome to. And then of course you can contribute. All right, so the next couple of slides are going to be on different subpackages for PlasmaPy and possibilities for mostly broader collaboration in the future, but also the essential functionality does have links to potential other PyHC projects. So our first subpackage, my favorite, is plasmapy.particles. And what plasmapy.particles includes are functions to access fundamental particle data. So things like whatever these are, standard atomic weight and things like that. Not things like collision cross sections yet that you can get through Chianti. So that's a hope for the future. We also have classes that represent both physical and custom particles. So if you want to create an iron 13 plus object, you can do that in PlasmaPy. And if you want to create a custom particle for doing something like a particle and cell simulation, that is also something that you can do. And we also have some helper functionality, including some decorators that can process particle inputs. We made this, we designed this to be compatible with astropy.units. And since a lot of heliophysics involves working with plasma that contains particles, the collaboration possibilities are pretty broad. So this is our most general functionality. And some of the examples are in situ composition measurements and spectroscopy, but there are a lot of others. The next collaboration possibility for a notebook is our plasmapy.formulary subpackage, which contains functions to calculate a whole bunch of different things like plasma parameters, dimensionless numbers like the Lundquist number, which is another one of my favorites, and then the horrible Brzezinski classical transport parameters. And by horrible, I mean wonderful. But we also designed this to be compatible with astropy.units. And the formulary is pretty straightforward to use and can be used in conjunction with in situ plasma observations and plasma simulations. And also if you want to figure out what regime a particular plasma is in, you can use this to calculate the numbers. And I should mention that Eric Grimes wrote a notebook pretty recently on using PlasmaPy to calculate plasma parameters based on data read in through PySpeedS. So that was really exciting to hear about. And then I think there are also some connections with Komodo in here also. All right, so now we're getting into stuff for more the future. So one of the packages that is currently in development is plasmapi.dispersion, and this is being developed to contain functionality to calculate wave and instability dispersion relations, both analytically and soon numerically. And the collaboration possibilities for this are most strongly related to in situ measurements and laboratory measurements of plasma waves. And this is work that's being done by a few University of Delaware students, including Ramiz Qudsi, who just graduated and is now in Boston, got to hang out with him on Sunday, Elliot Johnson, and Shane Brown. Another project which an intern is working on right now is adding magnetic topology tools to plasma data analysis. And this includes things like a null point finder and a finder for spine and separator magnetic field lines. So a lot of my research back when I did research was on reconnection. And this is some functionality that I've always been wanting to have openly available. And for this, some of the collaboration possibilities are analyzing simulations and also potentially in situ observations, which there are a couple of papers that find magnetic null points in, for example, Earth's magnetotail. All right, and then another collaboration possibility, and I'm really proud of the title, the new normalizations. Classes to represent the normalizations of different sets of equations used in plasma physics. So there are certain normalizations like to the Alfvén speed or to the plasma frequency, like in PIC simulations, or the cyclotron frequency, a whole bunch of things like that. And we want to have pretty broad functionality, like if you have a dimensionless representation of plasma with magnetic field, temperature, density, if you have a dimensional version of that, you can divide it by a normalization instance and get a dimensionless version of that. And since different simulations have different normalizations, it is a real headache to work between them, I discovered over the past 2 years for another project. So this is something that the new PlasmaPi simulation working group is working on. And the biggest application is for plasma simulations. And there's also potential for theory and like comparisons between simulations and actual measurements, in situ measurements. All right. So in terms of the hackathon tomorrow, probably the most straightforward possibilities would be representing particles with plasmapi.particles, hopefully with an application shared with other PyHC projects, and also calculation of plasma parameters with plasmapi.formulary, such as with the PySpeedS notebook that Eric Grimes created. And I'm terrible at responding to email, but I set up a calendar link so you can feel free to schedule meetings with me. And I'll put that into the chat momentarily. So, all right, that's what I have. So any thoughts? Oh, and David's point in the chat about combining magnetic topology stuff with PFS, with that package, magnetic model outputs, that would be great. So we should talk more about that.
Yeah, I was too excited to wait to ask a question or have a comment. But yeah, no, that sounds super cool. Yeah, maybe we should chat about that tomorrow.
Yeah, that would be great.
Great. Thanks, Nick. Any other comments, questions, clarifying questions? If not, feel free to put them in the chat for Nick later. And I believe the next tutorial brainstorming topic we have is for PySpeedS from Eric Grimes. Thanks, Nick.
All right, can you hear me?
Yep, sure can.
Oh, cool. All right, and hopefully you can see my screen. Before I jump in, I wanted to show that we do have a bunch of examples and tutorials already at SpeedS on our SpeedS GitHub. It's just github.com/SpeedS. And then you can scroll down and we have examples based on mission. So we have Themis- examples and MMS- examples. And we're still populating the Themis examples at the moment. But just to give an example, it's all Jupyter notebooks. You can click the all sky image or keyograms. And for the most part, we just copy and paste the examples over from IDL, from our IDL tools, and just reproduce the exact same plots. So if you're interested in the power of SpeedS and you're not familiar, or PySpeedS and you're not familiar, I suggest going to our GitHub page and browsing the examples repositories. And MMS obviously has a lot more examples. For instance, if you go under the advanced, you can find that notebook that Nick just mentioned, Plasma Calculations with Plasma Pi. It shows how to load the data, the FGM data, the FPI data, including with centering the measurements so that they're actually on the same timescales. And then actually extracting the data, interpolating the data values to a common set of times, extracting the data values, doing the calculations, adding units to the data, and then just passing those off to Plasma Pi to actually get the calculations. Right. That. So other PyHC projects that we're currently using and collaborating with, I mean, all of this depends on CDF-lib. So we're using that for reading the CDF files. And we're working with PyTplat to actually store the data and create the figures. And I just mentioned that we have examples now of using Plasma Pi to calculate plasma parameters with MMS data. I'm planning on adding other missions soon because we could easily add this for a lot of our missions. And we've been working on wrappers for the GeoPack project to bring the SIG and Yinko models into PyTplot. And in the future, I imagine these will also wrap the MPy code whenever it's available publicly and allow access to those models as well. And we're also planning on working on a new wrapper around the Happy Python client to bring the Happy data into PyTplot. And so potential tutorials, right now we don't have anything with PySat, so it'd be interesting to have some examples that combine data from PySpeedS with data for our, say, ionospheric data from ICON loaded with PySat. I think it's been on my personal to-do list to try to get data from PySat into PyTplot for a while now. So I think that one would be interesting. I think a PySpeedS plus SunPy notebook would be really interesting, starting with some event on the sun and using SunPy to show the image of some event, and then using PySpeedS to show how that event affects the magnetosphere. Another possibility is PySpeedS plus MagnetoVis. I think it would be really interesting to visualize spacecraft orbits from PySpeedS, or I'm not sure if it would actually work, but we also have, say, energetic neutral atom data, the statistically smooth sky map data. I think it would be interesting to project that onto a MagnetoVis visualization. And of course, there's also Plasma Pi examples with more missions. And I think Michael Hardinger has a whole bunch of load routines for various types of data. So I think just having a tutorial sit down with him probably could be pretty beneficial. But I was thinking about this, and it might make sense for me tomorrow to attend one of these other groups. For instance, I'm really interested in that Plasma Pi particles code, because we've been doing a lot of particle stuff. There might be some particle stuff we could move over to Plasma Pi that would be beneficial for everybody. So thoughts?
Hey Eric, this is Laura here. The PySpeedS and SunPy notebook is a really cool idea, having this kind of a event analysis thing for a whole workflow of, looking what's happening on the sun and than how it's kind of interacting with the near Earth environment and solar wind. So I think that would be something definitely of interest for tomorrow.
Cool.
Awesome. Any other thoughts, comments? I know there are some people typing in the general notes. Who was it? Tom B. Use with SpacePy. That could be interesting too.
Oh yeah, that's a really good one.
Yeah. Okay. Well, if no one else has any comments, we can go ahead and move on to the next set of tutorial ideas, which is based on SpacePy, and that will be given by Laura Hayes.
Did you say space?
I said space,
Yeah.
but I meant sun.
Yeah.
I just said SpacePy a second ago.
Yeah, cool. So yeah, I think we were talking about maybe doing something with Komodo. So I think Asher, you're online there. I see. Oh yeah. Do you want to maybe present or talk about what you were thinking?
Sure. Can you read me? Am I coming in?
Yeah.
Okay. Yeah. So yeah, I didn't really prepare slides. I do have a notebook that I've kind of started on the topic. So I'll try to share that. Oh, privacy, system privacy. Oh, does this mean I'll have to? I guess my Mac is not authorizing me to share right now, but here I'll just kind of talk about it then. So so Komodo is what we're looking at is making an interface between Komodo and SunPy, and the sort of the challenging thing here is that Komodo is a functional oriented, high level symbolic processing kind of toolkit, and SunPy is an object oriented, very data specific kind of world. So it's a very different styles of development and of how do we represent this a workflow in one system but allow it to be accessible from another system. So so what Komodo is really good at is working with functions. So basically, when we're working with simulation data, for example, or simulation output, we simply just need an interpolating function for any variable that the user wants to access. So and then Komodo, since Komodo understands how functions work, Komodo's automated plotting routines and function composition and unit conversion and derived variables, it has this whole system for dealing with things that have been registered as symbols in this kind of functional oriented paradigm. So basically, a Komodo object is a fancy dictionary that just registers registers functions with SymPy symbols. So SymPy is the underlying library that we're kind of mostly built on. And then another kind of large aspect of Komodo is the automated plotting, which I mentioned before is driven by this function inspection process, but we use Plotly as our front end. So that's another major difference between how Komodo works and how SymPy works, or SunPy. SunPy uses matplotlib as its kind of backend for plotting. And then, yeah, so thirdly, because some Komodo exposes these kind of underlying interpolators or whatever function is responsible for providing the data, it's meant to be able to, it allows users to access the raw data through that functional paradigm. So so SunPy, I've noticed a lot of SunPy's objects are kind of sort of hides the data from you somewhat. And so basically what we're kind of brainstorming is to like, how do we bring these two systems together? And what I had started with is just going through the main some of the intro to SunPy Jupyter notebooks and sort of commodifying the different parts of them so that they work at a super high level, and the user can basically do the same process but with fewer lines of code. So I think Rebecca wants to jump in here. She's been raising her hand. Go
Do
ahead.
you want me to share that what is Komodo slide as a visual?
Sure. Yeah, that would help.
Okay. Didn't want to throw you off.
I had like a whole, so I started kind of a tutorial GitHub project, and that's where we're gonna be developing this tomorrow, and I'll make sure that my screen sharing is working and all that. Is Rebecca able to share? Okay. Yeah, so this kind of, yeah, this is a sort of a good summary. So at the top right, you see that she's importing kind of the primary Komodo object from the Komodo library. This is a Python 3.7, and I think it might work on 3.6 even, project, but the only dependencies are really SymPy and Plotly, and I think NumPy as well. And then she's defining a function. In this case, it's techfunc, and she's decorating that function with this Komodify decorator. So in this functional oriented world, we deal a lot with like taking a function and like adding all kinds of like metadata or remixing how that function would work. And so we do that through defining these decorator things. So the idea is that it's a very simple way to augment so like say you have a given function, in this case, the techfunc, and it's just returning values from an interpolator, and it takes time as an input. Well, so the Komodify decorator adds units and adds, it looks like she's adding data as metadata from this dictionary of the tech data. And then it also defines argument units. So the input to the function should be in hours here. This is another way of difference between SymPy and Komodo, is that SymPy uses AstroPy units. Komodo uses SymPy's unit system because SymPy has a very, it has its own unit system, and we're built on SymPy, and keeping two different unit systems around is very complex. But a more practical difference is that in Komodo, units are attached to metadata of functions and not to the outputs of whatever the function's spitting out. So Komodo doesn't care what the object types passed around between functions are, at least up until the moment of plotting. So you can be passing around dogs and cats, and Komodo can just operate as normal so long as you can add and subtract and multiply dogs and cats. Then Komodo's unit system can handle it. And so Rebecca's worked a lot on AstroPy unit conversion to and from Komodo. So there are tools available to go between the systems if you need to. But the main thing is, so she created this Komodo object called ko, which is she's instantiated with by registering this tech symbol is just the name that she's given it. And then when you render this in a Jupyter notebook, like if you just put ko on a line by itself, then it comes out as a LaTeX rendered function. So, and there's functions to get the LaTeX string. And the idea there is that you want to be able to, you can take your workflow and copy and paste it directly into like a manuscript that you're preparing for publication. And by utilizing Komodo's automated plotting system, you can also start building up your manuscript and your plots from just quick look graphics. So you can see Komodo's, it looks like it's done some unit conversion in order to get this resulting plot. And so this is TC as a function of time. So this is it's a one-dimensional plot. Komodo has kind of a library of plotting routines that are kind of handpicked to go to support like contour plotting or 3D visualization. It can even handle like isosurfaces if you're clever about how you construct your isosurface. But it's sort of it's meant to be, you can switch out what types of plots go with what types of function signatures as well. So I think I've talked enough about it. I'll just sort of open the floor to kind of ideas and suggestions. Tomorrow you'll see where I've gotten with the notebook, but yeah, I think I'd like to get more input before.
Ooh, sorry. I have a quick question then. So in the slide you just showed, naively, it seems to me that the stuff listed you can kind of do in Matplotlib and SciPy already. So I was wondering if there were any really cool or interesting features in Komodo that I don't know about Komodo at all, so apologies if I missed them. But yeah, are there any really cool features that not easy
sure.
to do in Matplotlib?
Yeah, sure. The idea is that we're kind of geared toward so if you already know SciPy and you're just doing SciPy things, do SciPy things with SciPy. You don't need to Komodo for that, right? But the moment you are trying to get one project in a silo, kind of in a when you're trying to combine your analysis with another system, let's say you're getting your satellite positions from another thing, and you're trying to feed that into SciPy's coordinate transformations. Well, you don't necessarily need to learn either, for example, PySat, or you just need the commodified version of PySat, commodified version of SciPy, and it handles all the function compositions for you, the unit conversion, plotting, and all that stuff. So basically, the idea is if you're a high school teacher or you're doing a class of intro to space weather, space physics, you sort of just have this super high level GeoGebra kind of approach where a high schooler can jump in and just start doing physics. And then when they want to go deeper into the data and analysis, and they have hours and hours, if they're a grad student or they're paid to do something, then they can start getting into the underlying interfaces and really get the most out of it there. But yeah, to that end, it also lets you we try to containerize everything that we build, and so you could also use the Komodo API to connect systems that have completely different dependencies. So you can basically stream data between between the different containers, and Komodo, just as long as Komodo sees it as a function, then it doesn't care where that function's data is coming from. So that's another neat feature, but it's not something I really have time to go into.
Cool. Yeah, great. Yeah, that sounds really awesome. Thanks. Yeah.
Tom, you have your hand up?
Yeah, sure. You mentioned the issue of being able to get to a lower level access of the data, and for my stuff, I mean, I work very often. I'm trying to pull a lot of this data into tools that you guys don't even touch. So that's always been a bit of a challenge for doing some of the data viz stuff that I do and some of the tools that I use. But I would just like to say, emphasize that, yeah, it's nice to have that low level access to the data to be able to pull in numbers to build structures for tools that you haven't even thought of even using yet. So anyway, I just want to thank you for, keeping some of that stuff in consideration.
Yeah, absolutely. That was kind of a key thing so this kind of grew out of the CCMC's desire to have some way of getting people access to the underlying data with basically no a priori knowledge of the system. And I found that through working, because I was on the Chameleon project for many years, and and the main project was problem was we can give you the raw data, but almost nobody installed Chameleon because it's only the superpower users that actually would ever go through all the hurdles
Yes.
Right. So we wanted to sort of step back and say what's the simplest spot? Every physicist is taught how to manipulate expressions and how to write them down, and they always write units in bracket notation on the left hand side, and that they don't care what the formats is and all this hard work that goes into all this stuff. They just want results. It's faster than you can produce them. And so with this whole thing, it's been that's kind of been the bar that's sort of set for us. It's how do you teach someone physics who has no background in Python, for example? What if they just know LaTeX and they just want to write their manuscripts and they don't have time to do all that stuff? I mean, they can pay someone else to do the hard work, but so I think it just being able to leverage the fact that all these people know math, and then they just want to work with symbols is a way to kind of figure out what we need to really focus on, and that's when it comes down to like, well, what's really the function that you really need to have access for to get their foot in the door. So like with the sky coordinate class, like getting the 2 coordinates thing commodified was really just like setting up a simple object in that function, and then passing the arguments from like they could be numpy arrays, for example, and then do some reshuffling of the arrays and feed them in, and then just commodify that as decorate it with a function decorator. Like that's a super simple thing that a million people don't have to do every time. Like we can write a simple interface class that exposes things at that functional level. And then if they want to get more out of the sky coordinate class, they can then go and look at the documentation for SunPy and get deeper into it there.
Yeah. Although that creates the additional challenge that, like I because of my stuff is mostly in 3 dimensions, I'm often using Spice to do a lot of my coordinate transformation. So the question becomes, how well do these 2 coordinate system methods in separate packages, will they play nice together when I've, built a structure in using one tool and a structure in another tool, and they use 2 different coordinate mapping things. I mean, in principle, they should be very, very close, but
yeah, if you so what are the way we're doing it is just commodify all the things. So like, so we can build a commodified version of Spice, and we can do one of, like, we did that with like PySat, and yeah, we do end up using objects like arrays, like numpy arrays. They have to have shapes, they have to add them together and stuff, but that's just like the vast majority of what people want to do isn't so detailed. Like, no, they don't need to get into the nitty-gritty of like CDF formats and HDF5 and whatever. So yeah, we're just trying to find like what is low-hanging fruit here, and then and I think we can get a lot of like just flying a satellite through a model, right? Like you have what like it's like one is a function of its positions as a function of time, and another is like variable results as a function of position. Like so, and you should be able to compose those 2 together, but there's just virtually no tools out there for doing that in 2 lines, like without learning, without climbing this gigantic learning curve. Anyway, sorry,
That's okay.
had
Thanks.
Any more questions before we wrap?
I guess we can have a think again tomorrow about some workflows that we want to kind of show an example of with SunPy by doing all this commodifying of it. Like, let's think of something that would be useful to somebody to use. So if anybody has any ideas, that'd be great.
And if you don't have those ideas now, but think of them later today, feel free to put them in the general conference notes document. Well, awesome. Oh, go ahead.
I'll put a link to the Git repo for this the beginning of a beautiful thing, hopefully. So thank you.
Awesome. Thanks, Asher and Laura. Let's see. So the next person up for tutorial ideas is Russell with PySat.
Hello, everybody. Can you hear me?
Yep.
All right, great. Thank you. Let's see. I'll just share my full desktop. Okay, hopefully that's working.
Yep, sure is. Great.
So I just wanted to start out with some intro for PySat. I was hoping we get some new folks here, and it sounds like we do. So that's great. So yeah, I'm the founder of PySat. I'm now at Stoneris. I'm not the company I started. And of course, I'm not developing PySat by myself. I've been collaborating with Angeline Burrell and Jeff Cleansing with PySat for a long time now. And Jonathan Smith has been working on it for, I think, a few years now. So general problem space that PySat is going for is I'm just attacking the problems that all of us have in space sciences. Now we have a variety of data or models that we're going to be analyzing, and we want to do some kind of custom analysis with it, but because of all the different data and models that we have, it can be a challenge. You tend to write specific software for the data, and then that makes analysis challenging. If you want to take that analysis to another instrument or another model, you end up typically having to change a lot of things. So we're trying to attack that that general thing and provide PySat so you can load and interact with instrument model data in a general way. And then you can write analysis codes and stuff that work on any one of those supported instruments from PySat. So there is published work on PySat. Here's a graphical view of PySat as it is right now. So a couple versions back, PySat had everything all within PySat itself. It was kind of a very big package. With our current release, the version 3 series that we're on right now, we've taken all that functionality and where appropriate, broken it out into its own package. So PySat becomes just the general data and model interaction tools, and then all the actual support for different instruments and models and analysis are in their own separate packages. So where it's an ecosystem on its own. So that way, if somebody in the community wants to interact with it, interact with PySat, they can interact with it the same way that we do. So, right, the simple phrases like we're eating our own dog food. So it's not that we have special access to PySat when we're doing these things. We're trying to interact with it like we're on the outside. And with our public code that's on pip right now, it's PySat itself supports over 70 data sets. And if it wasn't just the public code and thing on pip, it would be probably around 90 or so. And that's distributed across different areas of space science and models. So like all these packages over here on the right, these are all data source plugins, space weathers, providing space weather indices from different places. PySat Madrigal provides generalized access to Madrigal data. PySat CDAC, again, we're building generalized tools to interact with CDAC, which is like the source of Cosmic and some other data sets. PySat NASA's generalized support for NASA, and models is here. We're providing support for models and analysis tools with working with models. And then over here, we have things that are reuse packages like PySat missions, where we can simulate orbits and missions, PySat seasons, which does analysis over seasonal timeframes, whatever those happen to be. And then there's also PySat Komodo, which it's a connection of Komodo with PySat. So PySat provides generalized access to data. Komodo says, hey, I will do whatever you want with whatever you give me. So Asher spent a little bit of time to just connect the things, the inputs from Komodo to the outputs from PySat. And that provides like basic 1D and other support for anything that PySat can load. So we can support large workflows. PySat's intended to be like a base package that people can use to do whatever thing that they want. So in this case, this is illustrating, hey, we're going to try to run TyGCM, but to run TyGCM, this model, we need space weather information. We may need instruments to do validation or pull things in to see TyGCM, things like that. These all come from a variety of sources, and you can use PySat and a variety of these packages to interact with all that, to set up the processing, manage the running, load the results back up, do your model validation and things like that. So there's a full-on data flow, which was developed as part of my instrument distribution, my science data distribution with my work with instrumentation. So as an instrumenter, when you send out data, you want to tell people, not all the data is always going to be clean. Here are the ways that you can clean it. But unfortunately, not everybody gets the message, or maybe they get the message, but by the time they start really working with the data and things like that, they forget, or there's some miscommunication. There's all kinds of reasons that there's a user may not be getting as clean of data as they may think. So as part of PySat, there's a variety of things. When a developer releases support for a particular data set, they have a variety of functions that they can put code in to make sure that the data is coming out in a way that a user may expect if they're expecting it to be clean. Now, PySat supports a variety of data levels. You can have no cleaning all the way up to clean, but by default, it goes to clean. So if you, as an instrumenter, if you provide support for your data set within PySat, you have some degree of default control of what a user is going to see when they load your data via PySat. And you can make sure that the clean is actually good, clean data. The fancy word is that this workflow is Turing complete, so you can do whatever you need to do to the data as it's being loaded before it's presented to the user. There's a lot of functionality. I don't have time for of course, all of this. So unfortunately, I'm not actually going to be available tomorrow. It's just something that came up yesterday, and I couldn't find another PySat person to stand in for me. So there's going to be some standing kind of topics that I'm presenting here for the hackathon. But the good news is there's a ton of documentation. So if I can switch from this to the actual documentation, here's a website. If I just start scrolling through, we've got a lot a lot of pages on a tutorial, how to use PySet, all the different things that you can do with it, how you add data, how you add metadata, how you control all kinds of settings for PySet, and how you load data, how you interact with it. We've got code examples, the more you know boxes, tables, all kinds of good stuff like that. All right, we'll go back to this. So, all right, so PySet, of course, is open source and open for contribution. So the general hackathon type topics that PySet always has is there are still plenty of data sets that PySet does not yet support. So even though we have generalized support for places like Madrigal and NASA, by choice, we've decided to not just provide blanket coverage for every instrument out there. We would like somebody who's familiar with that data set to come and say, hey, I'm going to add this data set to PySet. And then you can just use the generalized tools that are there and then add the specifics that are required for that package or for that data set, like the cleaning parameters. So you can provide some code to provide some cleaning. There's areas to provide like acknowledgements and references. So there's just a little bit of work that we would like a user to do to add data set support to PySet. So when a random user uses it, scientist or not, you know, by default, they're going to be getting good quality, clean data. So there's a lot of examples that I already have from our development, you know, from adding all the different instrument sources. So if there's somebody out there who's considering adding their data set to PySet support, like here's PySet NASA, we've got a full ecosystem of packages. This is under GitHub PySet organization. Here they all are. Just a couple to point out. So this is a PySet NASA one. Here's all the different instruments that right now are on the public release version. If you want to see how like IVN data is supported in Icon, then here's the file. So all the NASA instruments pretty much follow a very similar flow. So that's why we put it all together in a package. So there's all kinds of different data sources here already supported. So if you have a data set that looks anything like one of these, then you can use this as a reference to add it. Similarly for Madrigal, in the public release version, we've only got 3 so far, but here we've got a ground-based station. So if you want to load up like something like a ground-based station, here's a perfect example from Hikamarka. And then we have a variety of examples here in PySat Space Weather for adding an instrument from a variety of data sources. Some of these come from LASP and other places. All right. So that's like a general thing that's always standard for PySet. We're always appreciative of somebody coming along and adding their own data set. There's also a lot of integration opportunities. So just one example, another package that I've written is called OMMBV, and it generates basis vectors for expressing ion drifts in the geomagnetic basis. So that package itself is not like require PySet very much, I mean, at all. It's an independent thing. It does its field line tracing and all that on its own. But at the same time, I've added a little sub package within there that couples the outputs from OMMBV to any other data set using PySat as the intermediary to express that. So I just wanted to show you what that code looks like. So if you say like, just to throw out some packages, Plasma Pi, if you wanted to be able to add supports for anybody to add those plasma parameters to an instrument data set, if you wrote a PySat compatible routine, then that would work as a general case. So this is under my personal account, rstoneback OMMBV, right, GitHub. The sub package here is satellite.py. And this is actually used by the Icon and like Cosmic missions to couple my outputs to the satellite processing. But here's the function definition. The one requirement to make a PySat function is you just accept the PySat instrument object as the first argument. And then after that, you can add whatever you want. And in this case, I accept a latitude label, a longitude label, and an altitude label. Those are the 3 parameters that the OMMBV needs to do its underlying calculation. But for a data set, it can be called anything, right? So in this case, the inputs, the user just lets the function know these are the string labels for these, you know, for the content you're looking for. And within the package, I make one call to OMMBV. It does its thing. I get all the data back. I add the data to the instrument object, but just doing that, nobody's going to know what that data actually is, right? So the rest of the lines here is just adding the metadata information about that data also to the instrument object. Go through, add a bunch of metadata because there's a bunch of parameters, and then return. I'm done. So if you want to be able to enable users to use your package via PySet, you can write some very simple routines to make that possible. And now this routine would work with any instrument that is loadable via PySet. Okay. And then PySat can be connected to other packages as a data source. So like Komodo, PySat Komodo provides an example of this. You know, Komodo, as I was saying before, lets you do almost anything with anything. And PySat's there to provide all kinds of different data. So, you know, Asher is the one who actually did it, but provides some background on how you can connect to the generalized class parameters on the instrument object to do the things that you want as well. And then a final kind of standing hackathon topic is, you know, other data source packages could be used within PySet as a data source. So could potentially, you know, hook into PySpeedS or hook into SpunPy or something like that. And then everything that those packages support could be available within PySet, or of course, with the other way around, everything in PySet could become like available within PySpeedS. So those are the general kind of standing hackathon topics. So, and apologies for the late notice. I'm not going to be there, but I just can't help it this time.
Thanks for letting us know. Anyone have any comments, questions, suggestions for Russell?
I have a quick question about what you made a comment that you have a Turing complete form way of pre-processing. Kind of curious about that, and then second, I'm curious about like parallel loading of so for doing like longitudinal studies or long-term studies, being able to load multiple days at once. How do we do that, or are there projects underway to do that in PySet?
So that's one of the newer features in PySet is that we do support loading multiple days at once, and you just provide the date range that you want, and you can even iterate over like multi-day loads. You know, if you want to, you know, look at say 90 days, 3 days at a time with no overlap or some overlap, we've got parameters so you can iterate over all those things or just load those things individually, and it's all, you know, backwards compatible with the previous one. So yeah, that's a great question. I think that's a new feature, and PySet Seasons does have support for, you know, doing that automatic binning and things like that. And PySet now does also have support for Xarray and, you know, pandas, and the Xarray support's getting better, of course, with every commit, but it's in good shape in the release version. Dask is hoped. So I know Dask is the multiprocessor version of Pandas kind of, and it's something that Asher has brought up on multiple occasions. And that is absolutely the intent, is to, you know, the next data format that I plan to add is Dask. And then hopefully, you know, since we'll have 3 formats supported, then that should hopefully be enough to, you know, generalize to N data sets or some approximation thereof, right? So that's the idea. So thanks for the question. Yes, I can post the links. Sorry.
Oh, yep, there you go. Just gonna mention that one. Well, awesome. You may not be able to make it tomorrow, but I'll still make a room for the hackathon stuff tomorrow in case anyone's interested in starting on some of the ideas you mentioned.
Great, thank you. And of course, anybody can email me with questions. I'll put that in the chat as well. And then there's always the GitHub, and there's a Slack channel link on there too. So you can always get to us via that.
Awesome. I also included your email in the general conference notes. So many places to be found.
Yeah.
Let's see.
Thanks.
Yeah. Thanks, Russell.
Thank you.
Next up, we'll be hearing from David Stansby about HelioPy.
Right. Can you see my screen?
Yep.
Great. Can you see a full screen slide now?
Yep.
Yeah.
Awesome. Okay, cool. So hello everyone. So I'm going to talk a bit about HelioPy. Yeah, I guess. So I thought I'd start out just a quick bit about the status of HelioPy. So the scope of HelioPy is kind of 1D in situ heliospheric measurements. So my personal background is in solar wind stuff and tools to analyze them. But my plan with HelioPy in the very near future is to deprecate it and stop maintaining it. So there's a few reasons for this. So there's a lot of badly written code. This is code I wrote 5, 6 years ago when I was kind of new to Python, and there are much better ways of doing things now. I don't really enjoy working on it. It's kind of mainly me just working on it. A community hasn't appeared around it, and there are obvious ways to replace it. So I've got some tutorial suggestions for the replacements at the end of the slides, but I thought I'd just quickly go through how it's being replaced. So the data module is going to be fully replaced by the next major version of SumPy. And so that's going to have support for reading CDF files and searching and downloading data from the Coordinated Data Analysis Web, which is an interface to NASA's Space Physics Data Facility. And so that has a load of in-situ data and kind of the stuff we're interested in SumPy, and I'm personally interested in is kind of mainly Parker probes, so all the stuff. And so I thought I would quickly just show you a demo of what that will look like when SumPy 3.1 is released. So yeah, so this kind of goes through searching. So package imports at the top, and then we define a search range and the data product we want to, time range and the data product we want to search for. And then we can run that search, and we can see that comes up with 7 results. And then we can just download the first result here, and that will download that CDF file. And then using the SumPy time series object, we can really easily just load that into a time series object and have a quick look at the data. So yeah, that kind of basically replaces most of the functionality in heliopy.data and kind of has the advantage of you don't have to, if you're already used to using SumPy and doing time series analysis in SumPy, you don't have to learn a slightly different interface for getting the data in another package, which was heliopy. The other main part of heliopy was heliopy.spice, and that kind of had 2 things. It had a database of SPICE trajectory kernels that were available on the internet. And it also had functionality for basically taking a SPICE kernel and sampling that trajectory and exporting a sky coordinate, so an AstroPy sky coordinate. And it builds on SpicyPy, which is kind of deliberately a direct wrapper around the C SPICE library. So it's kind of like a higher level above that library. So as far as I know, this functionality isn't duplicated elsewhere in another package. If it is, please let me know after I've finished talking. And my plan is to move that to its own package. So it'll be called something like Spice Chords, AstroPy Spice, or Astro Spice, or again, if you have suggestions, I'd be super interested in hearing them. So that's my kind of brief what's happening with heliopy. So ideas for this week I had were to clean up or add to existing SumPy time series tutorials, and kind of alongside that, try and look at integrating SolarWind data load in SumPy with other packages. So I think a couple of people have mentioned that, but yeah, if you have any ideas of, I personally don't have experience using SolarWind data in the context of like maybe more geospatial data. So if you have ideas, I'd be super keen to work on that with you. And perhaps also looking at writing a SPICE kernel to AstroPy and SumPy coordinates tutorial as well. So yeah, that was really quick, but that was all I had to say, really.
I echo what Michael said in the chat. Sounds like a good transition plan. Let's see, anyone have any comments, questions? Oh, from Nick. I'm curious if there are potential links with PolyAstro.
Yes, so I think PolyAstro, as far as PolyAstro is a package for, I'll quote direct from their website, for interactive astrodynamics and orbital mechanics. So I think they have a lot of analytical and plotting capabilities, and they have support for planetary SPICE stuff, but I'm not sure what their support is for individual Spice kernels. Thanks for mentioning it though, because I hadn't thought of it. And actually maybe adding that functionality to polyastro is a good way to go instead of starting a new package.
Maybe I don't know much about polyastro, so it's at
Yeah,
least worth looking into.
Yeah, I
So
don't
thank you.
either.
Sure. Well, thanks, David. I guess my question to people who have been in this community longer than I, because I actually wasn't one of the main founding members of it. So HelioPy was one of our core packages, and obviously now that's going to be deprecated or maintained, will be going. What was the original plan when it came to how we officially add a new package to our core packages as opposed to just other? I know, for example, in the past, we brought up potentially having PySpeedas added. I was just curious to hear from those who were here before me on thoughts on that. Maybe we can decide on some kind of structure for that now going forward.
I don't think there was an original plan. I think we need a plan.
Yeah.
Okay, well, let's discuss it.
I think from my point of view, I suggested it with the core package, and that was basically the process. When I completely agree, there should be more than that in terms of process. And yeah, I think it would be really good to have a discussion about what goes in the core packages.
For sure. Well, we have 20 minutes left if anyone wants to think about it and just kind of ideate. Yeah. Probably easier when we all first started and there were just a few people. Now we've grown a bit.
Yeah, so I think this, if that's all right, if I talk, I think this topic kind of came up on that document thing that we've been writing from that last meeting. I don't remember exactly what that thing was called, but it wasn't, you know what I'm talking about?
We're talking about the integration strategy meeting?
I think
Yeah.
so.
Right.
Yeah.
Okay.
Yeah, so that kind of came up. So and ended up being associated with it. So I just put a few thoughts down. And it ended with, hey, we should actually talk about this. So this is, I guess good timing. But the few thoughts that I had were, we could have a review system, whether or not a package then officially becomes part of PyHC. And I don't think the review should really be so much on content, but just on like standard site compliance. Like, does the package do the things that it say it's going to do? Is it, documented and stuff like that? So I'm very sensitive. On one hand, I want PySet to be expansive, but I don't want to take away from anybody else's. So that's part of, the design. Open source allows for a lot of different experimentation and things like that. And I think we should encourage that and let the market kind of sort out what's good and what's not. So for any kind of review or admittance, I don't think it should be so much content specific. Just, hey, if it's unit tested, documented, all that other stuff. And we could start out with perhaps, the packages that are considered core now or already the most far along. Use those developers as a selection pool to get a review committee to look at a new package. And if they, if it gets through the review system with approval, then it becomes part of PyHC, and then the developers of that package now also get added to the pool of potential, reviewers.
One issue
go ahead.
One issue that I realized is early on is one of scope. A lot of the entries in the list of packages are really for very specific tasks, and that's fine, and we want those, but I think the things that are in the core packages ought to have a sense of a larger scope. Now, how to define that is perhaps a little bit nebulous, but it's not just a one-off, this reads this data from this spacecraft and does this thing to it. It's a broad approach that reads lots of things and does lots of generic things. That was my idea anyway, what a core package was.
I would agree. I think a combination of the two is the best, that has wide functionality for a package, but also, follows all of our standards and meets them.
What happens to
certainly.
long-term? Go ahead, Aaron.
I was saying I'm the guilty one. I think
Certainly
of
the-
all those task-specific things, and I'm happy to think about, whether they should be delisted or put somewhere else. whatever seems appropriate. But, like say if you wanted to read Themis all sky data, like it took a fair amount of work to do that. And I didn't want someone to have to repeat that. I wanted them to be able to find that and just say, hey, I want to load, enormous amounts of Themis all sky data across a date range or something. Anyway, that's maybe a separate discussion.
One of the challenges with a lot of this stuff is some of these things started in pieces run by an individual, and as that person goes to other projects or retires or whatever, the question of support for some of these codes becomes a question. I mean, I started doing Python and Solar stuff back in the early 2000s when I started doing the data viz for the studio. And I mean, I was using Python 1.6 and, it was still, what is it, NumPy, there was NumArray, there was another numerics package and stuff like that. And I've watched these things evolve and had to shuffle code around and stuff like that. So, you make a package at a given time, you integrate it into something, someone else wants to access older data, and they find out that all the standards for accessing that data format have changed in some weird way, and they can't make it work. But I mean, that's one of the challenges I've encountered of doing this stuff for a very long time. And I've watched these packages where I've used something and then the package stops being supported.
Yeah, I wonder if that's like something to have like an attic or something like that, an attic or an archive. Like this is how to do, at least if like sometimes right here's a much more common issue is we have some IDL code to do something.
Oh, yes.
It doesn't work. Maybe it doesn't even work with the current versions of IDL anymore. Right. But at least if you know how it was done, and there was a package, I think, was it MPy? I forgot the one that started from Java. Of course, the Java code was working, but at least if you have a place to start from, this worked back in Python 1.8 or 1.6. At least if you know where to start, and so maybe that attic or archive or something like that.
Yeah. That's a whole heavy duty task in and of itself. Is trying to keep that stuff together. And then disk storage for all this content. I mean, it'd be nice to have, a common, right now, a lot of people have some of these codes hosted in their personal GitHub repository. So, I mean, yeah. The question of how to do a grand unification.
Right. Like I wrote a couple dozen Python packages that I think are some of the clutter people talk about here. It's like I did it during my thesis, and it's like, I had to use all these instruments, and I had to do, but it's like I didn't want to just discard that somewhere. But but on the other hand, I don't know if I can maintain them all to the highest quality. Like 28 packages or whatever. But if there was some, I don't know, this is just a random proposal that the group would have to think about. Some kind of attic or archive. Yeah.
Because I'm kind of the weird issue.
Put that as a feature in a package that's maintained more permanently. You'll have to choose which one. So kind of like HelioPy is doing. Right.
Yeah, it's kind of dividing itself up among other packages, and that it was I think SunPy or whatever he was saying. Because some of this stuff would be a good fit for PySat, because I had a lot of instruments, like I was using MMS, DMSP, Themis, all kinds of stuff, and those might be natural fits for PySat, for example. A lot of those instrumentation stuff, because that's a lot of PySat's mission too, is like take, as I understand it, is take like a position and range of times and pick instruments and put them all in a common coordinate system. That's where even though I've done specific things, a lot of that work is duplicated, this coordinate transforms and stuff, and that could be stripped down as they were doing with HelioPy to fit in I say PySat would be a prime example.
Yeah, I was the one who mentioned it earlier about SpacePy, and I don't, is that even supported anymore? I mean, I've looked through my stuff here, and I see that I'm only using the CDF reader from it.
It is supported.
Yeah, I used to use SpacePy just for that as well, and I've usually been able to use CDFlib, which is more a pure Python plus NumPy package. So I've been using CDFlib.
I might need to look at mapping that over then.
Yeah, it's because this with CDFlib, you don't have to install the CDF compiled library first, because it just uses this NumPy to do it, to sort of crack the CDF data down into arrays and stuff.
How is that speed wise? Is it as fast as
No, it's
No.
slower. And so the
Yeah.
SpacePy one does use the C library, but it's also more Pythonic. So, and they're working on making it more easy to install or whatever.
I think the bats or us part is kind of the bigger piece there, which is and I think Dan Welling is resuming leading that project. He's pretty busy now, but I wouldn't count it out just yet.
Yeah, SpacePy also, you think it's the Lawrence Livermore stuff is not accessible. So, but it has all been moved to external stuff. But I think there's a lot of pointers still going to the old addresses that don't work. So.
Yeah.
But the comment about at least containerizing it is is very helpful. I think there's a lot of if you can like build a Docker file and just like stick it in there, it's fine if it collects dust over the years. At least we can reproduce the results of like your publications and things. Like it's keeping that provenance is kind of more important than long-term sustainability of a package, I think.
Well, for the stuff that I did, like say these 28 or whatever packages I have cluttering up here, you know, if I think for them it'd be even simpler, just a pip file.lock or requirements.txt. Because I'm really, it's basically just Python plus a wide range of NumPy and maybe Xarray. So there's kind of a, what if I don't want to like contradict here with that, but I'm just saying these are very thin and light packages that just do one thing. So if I did just do a lock, like pip file lock, maybe that would be another way.
That might be mostly sufficient. It's just that you're relying on the registry of the PyPy registry to maintain that in perpetuity. And this is really, I think, like a real challenge. It's like, we have all this great kind of distributed or decentralized or whatever you call it. Like we have like all of these great packages and they're all sitting on people's machines. But then if you like, if that version isn't on pip anymore and you lock it, like no one can reproduce your results anymore.
Okay. Sorry, I was coming up with a strong man there. Okay.
I also wanted to mention, I put in the chat, the Software Sustainability Institute, and they have a lot of resources on like topics related to this discussion about long-term sustainability of scientific software. So kind of along those lines, I was thinking that this would be a good topic for a Helio decadal review paper. I might have actually signed up for it already. So we'll keep talking about it, I think.
Excellent.
Cool. Any other thoughts on this topic? Thanks everyone for your ideas and discussion.
I've got a question about Docker. Is there, so I don't know that much about it. So as let's take a working scientist, is there like a one-line command that they can use to say like, oh, to reproduce my environment in Docker, then this one-line command will just generate whatever file is needed to describe the environment, and that's it? Because I think most scientists are not going to, like, they don't want to be bothered by this, right? Unless it's some kind of requirement. And if it is a requirement, it should be very, very simple to fulfill. So does such a command exist?
Yeah, I mean, I prefer the Docker Compose kind of way where that will both build your build the environments, but also like weave together multiple services that are, if you have multiple different containers, like one for PySat, one for SunPy, one for, because like these dependencies are often conflicting. So basically what we do is we build a specific container for things, and then you can push those to repositories, either like registries, either under your control, or you can rely on Docker Hub. But the challenge is, the thing is, it's fewer requirements. That's the kind of the point. Like you don't actually need to install anything yourself except for Docker or something equivalent to Docker. There's other, like Podman or one of these other like services or containers.
Yes, I understand it. The question is ease of use.
Yes.
Yeah,
So
yeah.
Yes.
So basically, with
I just-
no knowledge of Python or any libraries, you can with one line install like SunPy onto your system. Like if you have Docker installed, which is like a 5-minute thing. So like in terms of ease of use, I don't know how else to compare it to. Like whatever we're currently doing is way more complex than like using Docker. Like and we've done this like with space space weather summer schools, where like we all these students haven't programmed at all, but we have Docker installed on their systems, and it takes like they can just jump into the tutorials. But yeah, it's kind of a bigger conversation maybe, or like a longer discussion about the pros and cons there. But like, but it does give you that like that some archival, basically a Docker container is just a tar file, but it includes all of the dependencies and everything in it, and it hides it all from you. And so you can export that as a tar file and ship it to and put it on a disk, and then throw that in a vault or whatever for 100 years, and then you can reproduce that environment later is kind of the point. Because it's really like, even like we have getting the data storage is hard, right? But like the whole environment for actually reading or doing anything useful with the data, like I mean, and we don't want to fall into like the with like the node, the way like node package manager works, like an npm in like the whole JavaScript world, that like moves so fast that you can't reproduce any environments from 5 years ago even. Because like all of the repos, like every time you try to install something, it's like, oh, there's security vulnerabilities everywhere, like you just don't maintaining that anymore, like good luck, you know. So I think we could easily fall into that with Python. Like the new version of NumPy doesn't support like most of our packages aren't going to be compatible with that. So like it just, even NumPy is moving so fast now. But yeah, just having like an old school like version of when you wrote your manuscript, if you could put all of that in a container that people can just load, like that would be sweet. But yeah.
Is Docker really that stable?
I mean, there's multiple implementation, like there's Docker, there's the HPC folks have a different Singularity is another approach.
Is my container going to work 10 years from now?
It should. It'll work better than whatever you're currently doing. Let's put it that way.
I don't know. I mean, I have a load of packages that very often have to play nice together on there. I mean, the issue of compatibility, I was only able to move to Python 3 about 2 years ago because all the dependencies that I had finally were available. And this is kind of a question, is, the ability to and now you've just told me something here about NumPy. I'm sort of like, now I'm scared again. What am I going to be stuck at for the next, few years?
Yeah, my point is like, you don't have to be scared if like you could have all of your stuff in Python 2.7, and if it worked then and you containerized it, it'll work in the future. It's just that it won't include all the new bells and whistles or security fixes, but it's stuck in a container anyway, so it's supposed to not be able to affect your system. I mean, there's caveats to that, but like you don't have to just upgrade for the sake of upgrading if you have something that works and you don't have the labor to support like porting every single thing that you wrote 10 years or 20 years ago into the latest and greatest. Like it's you have to like choose your battles. And like that's kind of my like, just through like trying to keep up with stuff, and you're one person and you have limited time on this planet, and it's like I don't want to be like porting stuff for the rest of my life. But anyway, that's my rant.
Welcome to my world. Yeah, because I've heard of Docker, but now you said there's some tutorial that like the space weather students do. I'd be interested in a pointer to that, just to find, because there are so many tools that have changed since I first started doing this stuff using Python, and I don't even use Jupyter notebooks. I mean, I started playing with them because there's certain interesting little features, but I still do most stuff from scripts because it's something that I start running and then I walk away, and a day later there's rendered frames on another computer.
Well, if you come by our tutorial tomorrow, I'm gonna show like, hopefully I'm gonna have this container running SunPy and Komodo in the same container. But
Okay.
what I really like is Jupytext, which is sort of the best of both worlds between scripts and notebooks. So you basically can write a script in a Jupyter notebook, but it's saved as a Python script and not a notebook. So which
Oh.
means you can actually put it on GitHub, and you can it also supports Markdown. So if you're doing like writing documentation in Markdown, you can execute the Markdown as Jupyter Notebook cells, but it's saved as a Markdown file. So you can just like put it directly onto your GitHub and it renders nicely. So that's what I'm doing or starting with our with Laura and I's tutorial. So and it's going to have a Docker compose and Docker files. So basically that means like if you have Docker installed, you can run it. But otherwise you have to use Conda and build from there.
Complicated or complicated?
Yeah, I actually rebuilt the PySat container because PySat's version 3. I'm forgetting, but I had containerized it previously, and now they've got a bunch of new bells and whistles. So you can check out the PySat Komodo repo for examples of containerization.
Awesome. Great discussion, guys. I love Docker. I'm all for it. Well, we're sorry.
I'm still trying to figure out what it is. I mean, other than some kind of container system, but there was Python had a wrapper thing that would go and like turn all your scripts into a standalone application, and this sounds like an extension of that capability, but it's more like an environment. Like I started using the Conda environments, which I actually kind of like now that I've gotten into them. But now that I understand them, and I've got like 3, I could probably run 2.7 again, but I don't.
Rebecca let Conda in a box.
Oh.
Exactly. Well, we have less than a minute until 11. If people want to stay on and keep chatting, you're free to do so, but I will officially say that today has wrapped up and we're done, and see you all again tomorrow at 9 a.m. for hackathons, Mountain Time.
Okay.
Thanks all.
Thank you.
Thank you. Bye, everyone.
Bye.
Bye.